So, good morning, everyone. My name is Musa Marcusso. I'm a PhD student at the Bosch Corporate Research Center in Training in Germany, and I'm going to talk about the project I've helped create and been involved in the last few years, which is the Unmanned Underwater Vehicle Simulator using Gazebo and ROS. So the UV simulator is part of a larger project. It was part of a larger project. It was created inside the EU project Swarms, which is a project that intended, under other objectives, it intended to improve the autonomy of the underwater vehicles, so it would be possible, for example, to easily deploy multiple vehicles to execute a very complex mission and in a cooperative manner, or to also give assistance functions to ROV pilots that would have to do intervention tasks with hydraulic manipulators underwater. So some questions arise back then, especially on where would be the test bench for all these new algorithms that are going to be developed in the Swarms project. First of all, testing the algorithms for underwater manipulation. How do you make the proof of concept that is actually going to help the pilot, and before actually going to the expensive hardware? And planning the mission strategy. So it's very important to know exactly where you're deploying those vehicles, if they have a safe workspace to work on, because if you have multiple vehicles at the same time, you don't want them to collide with each other, which would be very, very expensive. And especially one of the topics was that some algorithms that were planned to be developed would require replanning of the missions regarding the detections of some types of disturbances, such as strong currents, for example, or failure scenarios where you have actuators failing or sensors failing during the mission. So how do you safely do that in a way that is not going to put in risk all the hardware? So the simulation was a very easy conclusion to come to in this case. So the mission, under other reasons, is also because the mission for real underwater robots, especially if you have multiple ones, is very expensive and time consuming. And the communication during the mission, if you want to monitor what's going on, even in best case scenarios, the communication is very sparse, so it's acoustic based. And you cannot rely on that to react upon emergency situations. Collision avoidance is also difficult because perception underwater is very limited, and it's difficult to repeat and reproduce scenarios where you have some environmental phenomena going on. So if your algorithm has to react to some environmental phenomena, doing that in real life and testing out of software can be very tricky. So evaluation through simulation was deemed as crucial in the project. And with that, the UV simulator was created, and it was published in November from 2016 in GitHub, and it's still in development. And it's basically a set of packages, mostly Gazebo plugins and a number of ROS nodes that were published to enable the simulation of underwater vehicles using Gazebo. And some of the packages, there are a number of packages right now, but some of the packages is mainly the UV simulator itself, with mostly the Gazebo plugins that I mentioned for hydrodynamic, hydrostatic forces simulation, for actuator simulation, sensor simulation, so on. The Plum Simulator that I'm going to get into later, and UV manipulators that enable the simulation of intervention tasks underwater. Apart from that, a number of vehicles have already been published as well, so both torpedo-shaped AUVs and thruster actuator ROVs, which can also be used with the simulation. So some examples of the plugins are divided in 4 categories. There are more packages that can be seen in the repository, but I divided them into Gazebo plugins, sensor plugins, command and control, and world plugins. So the first plugin that is the most important one is the underwater object plugin, which is an implementation of the Fossen equations of motions for marine crafts, and basically it still uses the physics engine Gazebo for rigid body dynamics and contact forces, but it adds upon it the added mass and linear and nonlinear damping forces and buoyancy forces that are necessary to simulate this vehicle's interaction in the fluid. There are some implementation aspects that I would be happy to talk about after the presentation, especially regarding the added mass forces that need some handling so that the simulation doesn't go completely unstable. But it works for our purposes, and it can be completely configured in the RDF file. So the next important part is the thruster and fin plugins, because these are the most common actuators for underwater vehicles, and we needed to figure out a way to make it easily reproducible in Gazebo. So thrusters and fins have basically a dynamic, the thrusters, for example, have a dynamic model for the propeller's angular velocity, and it's fed on a steady state function, because the model, the actual model is very, it's highly nonlinear, is hard also to parameterize. So usually what you get from manufacturers is a steady state function that you can convert then the angular velocity, the current angular velocity of the vehicle to thruster output. The fins are similar in a similar way, but is instead as the joint angle, so you can calculate with that the angle of attack and feed that into the lift and drag model. One of them being the adapted from Gazebo's that's already available, and another one is the quadratic model for the lift and drag output. And this allows finned robots to be maneuvered when they are moving. Another important part is for world plugin is the current velocity plugin. So it at least adds some kind of realism to the simulation, since you are not often going to be throwing your robot in still water. So this plugin basically generates a 3D current velocity topic that all the robots that have the underwater object plugin subscribe to, and they can be either constant currents, or you can set up first order Gauss-Markov processes for magnitude and or horizontal and vertical angles, so you can add some kind of variation to the current during the simulation, which will actually help a lot for the next topic, for the Plum Simulator topic. So the Plum Simulation was one of the topics that was most important for the final demonstration of the SWARMS project. Is basically, one plume is just a fluid moving inside another fluid, so you have a column of fluid moving. And this is a very common scenario where you deploy robots to find this column of fluid inside in seawater, for example. So what we did is implementation of a paper that's cited down there, which is basically a source generates a number of dynamic particles, and these particles are subject to current, and also have a buoyancy and dispersion coefficient that you can set up. So you can, for example, simulate an oil spill or fresh water inside seawater. And this is only limited by a bounding box so that the memory doesn't explode with a bunch of plume particles. But this is possible then to detect, to at least simulate some environmental phenomena in using Gazebo and ROS. And additionally to that, one of the sensor plugins we developed was a particle concentration sensor, also based on the same paper, which is basically, it will, inside a sphere around the sensor's frame, it will detect all the particles that are inside the sphere, and then regarding the distance to the sensor at the time of creation of those particles, we can compute a simulated concentration value that can be used. So for example, if you have an algorithm that needs to detect if you're inside the plume or if you cross the plume or not, you can use that sensor, for instance, and it's going to be used in a use case later on. Another node that is really helpful is a thruster manager. Is a simple force allocation node that reads the TF frame and then checks all the transformations between the base link of the vehicle to each one of the thruster frames. And this is not rocket science, but it's one thing that many underwater simulators that we have saw before, we had to compute this by hand before, and this is just a node that runs on with the simulation and computes this for you, so the force allocation is dealt with. And the last package I want to talk about is trajectory control. It's a basic but important package because it not only contains several controllers common for thruster actuated vehicles, such as motor free, sliding mode, PID, and so on. AUVs have a geometric PD-based controller that can be used as well. But the most important part is that it has a Python API where it already contains all the interfaces to all the services and topics you need. So you just need to implement the controller logic itself. So expanding the system to your controllers and using exactly the same services is actually very easy. And it also contains some helpful waypoint interpolators, as they use a splines or Dobbins path algorithm, depending on your approach. So I'm going to present now some of the use cases we used basically in the Swarms project. This was the second Swarms demonstration mission in Mangalia, Romania. So the idea was also always to have a simulated demonstration and a real demonstration. And the simulated demonstration was helpful because with that you managed to actually show in very high detail how the algorithm was supposed to work, especially in situations where you have, for example, thruster failure, where you don't really want the real robot to go through, because if you lose one robot, you might lose $2 million. So in this scenario, you had 8 underwater vehicles by the coast of Mangalia, and they had to do a cooperative seabed mapping task, which was a very simple task, but it just showed how the functionality of the robot system onboard architecture developed by ONU departments works. So this is only one shot of Gazebo. So we built just a large world containing the coastline of Mangalia and 2 vessels marking the deployment points for the 8 underwater vehicles we wanted to deploy, and it was basically 2 large areas from 400 by 400 meters. And the RSOA system, what it does, it just divided the larger areas and assigned each one of the vehicles its own area to do the mapping. So here you can see just as adapted from the laser scan sensor plugin, and it's just showing that each one of them has the same side scanners, and they at the end of the day can stitch them together and make a larger map from the seabed. And it was very fun to see how many vehicles Gazebo actually could actually put up with. The next use case was related to the plume tracking simulation. So this large gray volume here is supposed to be a large volume of seawater, and these particles are supposed to be a freshwater plume, a freshwater column that's going through it. And the objective was to throw 3 different torpedo-shaped AUVs in the water, which is actually done also in real life, but in different depths, and they had to find the plume using salinity measurements, which is derived from the particles to concentration. So if you have fresh water, the more particles you have, the salinity will drop. So it will detect that it crossed the plume, and it will try to stay inside the plume for as long as possible, so it can actually track where the plume is going to. So this is only showing which vehicles were involved with this. The surface vessel in real life was a communication relay, but then in the simulation it's just hovering on the surface. And the 3 the LAUVs, the light autonomous vehicles, are Noctilus 1 and 2 from LSTS from Porto University, and Fridio from NTNU. So you can see here that the vehicles are going to, no, if the computer cooperates. So the EUVs, as soon as they enter the plume, they try to figure out a way to go back to the plume, so they can stay inside the body of the plume for as long as possible. So on the right-hand side is the simulated salinity values from the time. And this actually, the plume, this plume was used also in the Rio mission, because throwing things in the water and trying to track them is something you cannot control very well. So using simulated plumes is much better. And this was the third and final demonstration, was just a demonstration of using fiducial markers on the subsea panel. So one of the biggest issues with the piloting this robots is the pilot doesn't have very good depth awareness. So fine-tuning the position of end effector to turn the valve or handle something is very complicated. So these markers help to set up, as soon as they approach the valve, it would just snap to the position orientation needed to be, and it just had to approach it and do the job. And this is still something that this is just a proof of concept in simulation that was not done in the real robot, but it's nice to see that it works. Apart from the fact that it's missing a lot of underwater effects that could have done the camera detection very complicated. So just some future steps. So the SWARMS project is actually over. It's ended this July in 2018. And but the UV simulator project is continued as an open source project. It has a surprising number of people using it, and I just after my PhD is finished, I want to keep doing this project later on. And some improvements that I've been putting off for a long time, but I want to do soon, is improving sensor plug, especially acoustic based, or not the focus until now. Scenarios, underwater visual effects such as particles floating around or light damping, which is very important, and improving the underwater manipulation packages to make the intervention missions more realistic. And I just put the list of some of the links to some of the existing packages and for the documentation website. And just some acknowledgements to all people that made this also possible, with some of the colleagues from Bosch, Sebastian, Louis, and Thomas, which contributed with code and also 3D models. SWARMS partners, especially vehicle providers such as the ECA Group and the Zistec, which were nice and gave not only the authorization to publish their meshes and the vehicle parameters, but also contributed on giving feedback of how the function they're working. Other partners also make very, very important bug reports, which I'm very grateful for, and other contributors on GitHub, which make a large amount of pull requests. No. So, thank you very much.
Questions? Did you have a chance to do any physical validation?
We had some comparisons with the AUVs because we had contact with the partners, yeah. And the biggest problem was basically that it's difficult to obtain the ground truth information for these vehicles. It's in the context we are working on. But for some AUVs, we made a comparison with data from the providers. But that still need to be worked on. Yes.
Okay. Oh, Andrew.
In your multi-robot simulations, I saw they were doing some Morena patterns, but they weren't colliding at all. Did they sell a different?
Yeah.
Repeat the question.
So the question was if the AUVs were if they were in different planes in the simulation. But yes, it would be best if they could detect each other and or at least communicate with each other to know if they have to divert from collision path. But unfortunately, the as I said, the perception system is not good enough for moving targets so that it's safe for them to actually be on the same plane. So they were assigned different depths, and so that the owners of those robots will also be happy.
All right, we're gonna have to stop it there for time. Thank you.